This is section 3.6, long time behavior 1, the transient case. We are now about halfway through chapter 3, so let's recap what we have done in the section so far and where we are heading to in the following sections. So of course we defined what are Markov chains, we saw examples, we did a lot of computations with transition probabilities. In particular, you did quite some computations in exercises with transition probabilities, so you are hopefully quite proficient there. And then we dealt with the concepts of recurrence and transience, which is about reaching certain states or returning to states a finite number of times or infinitely often, and things like this. And in the last section, we dealt with periodicity effects, which is about the effect that possibly you can not return to certain, to a certain state at points in time which are outside a certain period. Okay, and the remaining chapters or remaining sections 3.6 to 3.9 are about the long time behavior of Markov chains. And in order to see what we're going to do, let's take a look at some introductory examples. So here there's some tiny example on this page. You see this Markov chain consisting of two states, 0 and 1. And imagine p is very small. So with a very small probability, you leave the state 1 and then you immediately return to state 1. Yeah? When you let the Markov chain run for a very long time and then ask, well, say at time 1 million, am I at state 0 or am I at state 1? Then, of course, with very high probability, you will be at state 1. Yeah, because anyway, when you are at 1 with high probability, you stay at 1. And if you're at 0, then, which you are not very often anyway, then you immediately return to 1. Okay, so of course, it's clear that with very high probability, you are at 1. So qualitatively, it's clear what is going on, but we want to quantify this. Yeah, we want really the probability that at time n, when n is large, you are at 1. Okay, when n tends to infinity, we want to see what is the behavior of this probability. Yeah? So this is what I mean by long time behavior, and we have to deal with this in several steps. This section will deal with a transient case. So when a state j is transient, which is not the case in my example here, but of course we've seen examples of transient states, and then we will see what is the probability to be at the transient state after a long time. And we will see that this probability tends to 0, actually. And then a second part of this section is sort of a lemma that shows a technical result, namely that in an aperiodic class, Pijn is positive for n large enough. Yeah, then it's sort of mixing. Yeah, you start at a state, and it may be complicated to reach j, and it may be complicated to reach it after sort of 100 steps, but after 1,000 steps, for sure you can reach it always. Yeah, after 1,001 and so on. So this is this section, and then in section 3.9 we're going to see the corresponding result for the recurrent case. So, and this will be much more interesting than the transient case, and we have to prepare for this in sections 3.7 and 3.8. So we need another notion, the notion of an invariant measure or an invariant distribution, and we will see that there's a relation between these invariant measures and invariant distributions to the concepts of recurrence and transience. And once we've prepared this, then we can show the main result, also the main result of chapter 3, that in the recurrent case, the probability that xn equals a certain state converges to a certain quantity, and we can identify this quantity as coming from an invariant distribution, under certain assumptions, of course. So in particular, in the Markov chain that you see in front of you, we will be able to quantify what is the probability that after a long time you're at state 1 or at state 0. Okay, so that will have to wait until section 3.9. Here is the first main theorem of this section. So there's a transient state j and some other state I. And we ask for the probability that when we start at I, we are at j after n steps. So here's a repetition of the definition. Yeah, Pijn is nothing else but the probability that starting at I, you are at j after n steps. And we see that when n tends to infinity, this probability tends to 0. So in other words, wherever you start, yeah, I is arbitrary, the probability to be at state j is transient, after n steps tends to 0 when n tends to infinity. Let me visualize this with a picture. So you've seen this picture before. There's this red area and there's an exit from the red area. So you may start at 2 or you may start at some other place here. You wander around in this red area. Sooner or later you will be at 2, and then sooner or later, after a few visits to 2, you will take the exit and then you will not come back to the red area. Yeah, so all the states in the red area are transient, and the probability of being there after n steps tends to 0. Let's prove this theorem. First step is that we start with a transient state, and we want to show that Pjjn tends to 0. Okay, so that's the first argument. And it will be short enough to fit at the bottom of this page. So since j is transient, the probabilities Pjjn are summable. Yeah? This is the criterion for transience and recurrence. Yeah? So in the transient case, these sums are finite. In the recurrent case, they are infinite. And this, of course, implies that the things that you sum up here tend to 0. Yeah? Because otherwise it would not be summable. Yeah? So Pjjn tends to 0 when n tends to infinity. So when you start at j, the probability to return to j after n steps tends to 0 when n tends to infinity. The second step is a bit more work. We want to transfer this result to an arbitrary starting point. Yeah, I want to start at I, some state of the Markov chain, and I want to ask what's the probability of being at state j, the transient state, after n steps. This will be done in step 2, and I will use the following auxiliary notation. So Fij to the k will be the following probability. We start in I, and at time k, I'm at j. And before that, I didn't visit j. So I visit j for the first time at time k. So this is, as I said, the probability to reach j in k steps for the first time. As a next step, we're going to look at the following observation. So I'm claiming that the sum of the Fij k is Fij. Well, what was Fij? This was the probability that you start an I and that you ever reach j. So that there is an n from 1 to infinity such that xn equals j. Yeah? So the probability of ever reaching j when you start in I. So why is this the same as this sum here? Well, if you reach j, then you have to reach j at some time for the first time. Yeah, and on the left you basically make a decomposition into when you reach j for the first time. Yeah, you reach j either at k equal 1 for the first time, or at k equal 2, or at k equal 3, and so on. Okay, and these events of reaching j for the first time and at 5 is disjoint from the event that you reach j for the first time at 10, for example. Yeah, so these things are disjoint. So basically here you have the sum of probabilities of disjoint events, which by sigma additivity give you this event here, the probability of this event. Furthermore, notice that the right-hand side is a probability. So the probability is less or equal to 1. Yeah, so I'm going to write this here. This Fij is less or equal to 1, and we are going to use this. Now let's look at the final computation. Recall that we want to show that Pijn tends to 0. And if we sum this up in n, and we see that this is summable, then, well, we are done, because then we know that this has to tend to 0. Now I'm going to rewrite this probability here in a complicated way. Recall that this probability is the probability that starting in I, you reach j at time n. And now we decompose this and ask, when do you reach j for the first time? Yeah, so this here says, this additional condition here says that you didn't reach j in the time steps 1 up to k minus 1. You do reach j at time k, and then of course you reach j again at time n. Notice that this is a decomposition of this event. Yeah, so if you call these events here whatever bk, for example, then the union of the bk is for k from 1 to n is nothing else but the event that xn equals j. So basically we only use this observation and the sigma additivity of the probability measure. The next step is again a sort of conditioning. So after my handwritten modifications, these two lines should be exactly the same. So let's check. So forget about this first part, and then you see that there's xn equal j, which is copied from here, comma, xk equal j, and so on. And so this is really just copied from above. Now what I'm doing, I'm conditioning, so I'm putting a bar here, which means I'm dividing by this probability here. And since I'm dividing by this probability, I also have to multiply with this probability in order to compensate for this, and this gives me this line. Now what do we have here? This thing here is nothing else but the fijk from the top. Yeah, if you compare this is exactly this term. It's sorted the other way around, but it's exactly the same term. So this is fij to the k. How about the second term? In the second term, we have some initial distribution, which is here saying that we have to start at I. Then we do certain steps, and we forbid certain steps for at time 1, at time 2, and so on, up to time k minus 1. At time k, we are at j, so we know where we are at time k. And then we have to make a transition to xn being equal to j. And recall that essentially the Markov property says, if you know that at time k you are at j, then you can forget about everything else that you know before time k. Okay, so we put this into formulas in exercise 3.13, where we showed that you can leave off these conditions here as soon as you have sort of one point where you know what is going on. Okay, so drop these conditions here. This is what you can do by 3.13. And then this is just a probability that you start in j basically at time 0, yeah, not at time k. This is where you use 3.10. So you start at 0, and then at time n minus k, so you have to subtract k here also, you are again at j. So this is nothing else but the probability to start in j and to be at j at time n minus k. Okay? And as I said, I used 3.13 to get rid of this stuff here, and then 3.10 to move things back to the beginning, yeah, to basically subtract k from here and k from here. So this becomes n minus k. Yeah, and then I replace by the definition of the pjj to the n minus k transition probability. So now we have here two sums, and this looks quite ugly, and we don't know what to do with it. Then a good idea is always to exchange the two sums, which I can do because the terms that I'm summing up are non-negative. So I use Fubini's theorem to exchange the two sums. So now we have this k-sum here, which moved in front, and it's now a k-sum from 1 to infinity. And then there was a condition between k and n that k is less or equal to n. So the n sum that moves to the second position now has to start at k. So it goes from k to infinity. And then I sorted the terms a little bit. So this fijk is only depending on k, so I moved it out of the n sum. And then we have here the sum in n of pjjn minus k. And here, of course, we can make an index shift, yeah, because, well, we are subtracting k anyway. So we can call this n prime and have n prime run from 0 to infinity. Yeah, so this is the next line. So first we have the k-sum here of the Fijk, and if you look at the top here, this is exactly this sum. So this is less or equal 1 and certainly less than infinity. And the second sum here is also finite because, well, j is transient, and we already used that the criterion for transients tells us that this sum here has to be finite. Yeah, this is exactly the transients of j. And now we are finished because, well, we wanted to show that this thing is summable. If this thing is summable, then the individual Pijn have to tend to 0. And this is what we wanted to show. This finishes the first part of this lecture, where we wanted to show that for a transient state j, the transition probabilities Pijn tend to 0 when n tends to infinity. Now we start with the second part of this video, and the second part concerns only this technical lemma that you see here, and in a sense it's completely unrelated to what we have been doing so far. It just fits here time-wise, and we will need it in the later proofs. The lemma says the following. So assume you have two states in a communicating class, and the communicating class is supposed to be aperiodic. Communicating class in particular means that you can get from I to j, so Pijn is positive for some n, okay? And since you can also get back from j to I, then you will see that well, there is not only exactly one n such that this is positive, but well, there are sort of again and again a few n's, and you can single out a sequence that tends to infinity such that Pij is positive for some n. What we want to show here in this lemma is that this Pijn is positive for all n starting from some n0. Let me illustrate this at this graph here, which looks complicated, and it's deliberately complicated actually. So you have a state I where you want to start. You want to get to a state j. Clearly, after 1, 2, 3 steps, you can get from I to j. So Pij3 is positive. On the other hand, Pij4, for example, is 0, yeah, because after 4 steps, well, you are either here or here, but certainly you're not back to j. So the question is there an n or an n0 such that Pijn is positive for all n which are greater than n0? Okay, and this is an exercise, so please stop the video here, take a look at this graph and try to find n0 such that this is the case. So the lemma says there is always such a thing, and yeah, it's instructive to find this in a concrete graph. Okay, so let's take a look at my solution. In my opinion, n0 should be 9. So let me argue why I think this is the case. First of all, let's take a look at Pij5. So after 3 steps you are at j. After 4 steps you can be at either of these places. After 5 steps you can be at this place or at this place. So you cannot be back to j. So Pij5 is also 0. Now after 6 steps you can be back to j. Yeah? So Pij6 is positive. Yeah? So after 6 steps you are here or you are here. Now after 7 steps you can be here or you can be here or you can be here. Okay? And after 8 steps you are either here or here or here or here. Okay? And after 9 steps, well, if you go this way, you can be here, and you can also come this way. And actually, by taking this loop, you can be back here to j after 9 steps or after 10 steps. So you can just go for an extra round here and see that, well, for any n which is greater or equal 9, you can be back at j. Okay, so let's take a look at the proof of lemma 339. the first step we're going to do is to show that pjjn is positive for all n large enough, larger than some n0 tilde. And actually this will be the main step. Yeah, so you saw this also in the example. You get from I to j, and then the question is, can I get back to j at any frequency that I want? So the argument in this proof is rather algebraic, as you will see. So consider the set A of times such that pjjn is positive. Yeah, these are the times that we are interested in. Now, if the time 1 is in A, then actually I can come back after one step. I start it at j, and I can come back after one step, and then of course I can come back at any step that I want. Yeah, so in this case A is n, and we are done. Okay, so nothing to show. So let's assume that 1 is not in A. Now we use that the state j is aperiodic. And this shows that A is not something like 2n or something. Yeah, so it's not a grid. Or in other words, the greatest common divisor of the elements of the set A is 1. Yeah? If it were some other number, then all the elements in A would be divisible by that number, and then we would have a periodic. J would be periodic, yeah, which we assumed that it's not. So if the greatest common divisor of all elements of A is 1, then of course we find finitely many elements such that the greatest common divisor equals 1. Now I'm going to use a tool from algebra which says that you can always write the greatest common divisor of A1 up to AK as a linear combination of the A1 up to AK, yeah, with numbers in Z. So this is called the Euclidean algorithm, and we're going to practice this algorithm after the proof. So at this point, either look up the result in your algebra class or just take it for granted that you can do that. And after the proof, we're going to see this in a few examples. Yeah, I'm not going to prove this. I'm going to take this for granted here. Now put Z to be the sum of the AL. This sum is greater or equal to 2. Yeah, because the A's are not 1. Yeah, 1, the number 1 is not in A. So even if there's just one A, it has to be greater or equal to 2. The next step is to define our n0 tilde, and we define it by Z times Z minus 1 times the maximum of the CL. Notice that the CL are not all 0. Yeah? Otherwise this linear combination would be 0 and not 1. So this maximum here is at least 1. So this is greater or equal 1. Z minus 1 is also greater or equal 1 because Z is greater or equal to 2. So this whole expression is greater or equal to Z. Now for n greater or equal n0 tilde, we can write n as Z times x plus y, and y is between 0 and Z minus 1. So y is basically n mod Z, okay? And x is such that, well, Z times x plus this remainder, basically, when taking the mod with Z, gives us n. And the x here is greater or equal to 1 because n is greater or equal to Z. And actually a quick computation that you see here gives that x is even greater or equal to Z minus 1 times the maximum of the modulus of the CL. Yeah, so the computation is here. N is greater or equal to this thing here. N can be represented as Zx plus y. If you divide by Z, then x is greater or equal this number here, which is in minus 1 to 0, plus this number. So x has to be greater than this number here, yeah, because x is an integer. Let's use this. So consider the number x plus y times CL. So this is greater or equal. First of all, this term here comes from the comparison to x. Yeah, x is greater or equal this thing. So I'm estimating x by this. And CL can be negative, but CL is certainly greater or equal minus the maximum of the absolute values of the CL. if I unite this, then this is z minus 1 minus y times the maximum of the absolute values of the CL. And this is greater or equal 0 because, well, this maximum is not 0 and y is less or equal z minus 1. Yeah, so this whole thing is greater or equal to 0. Now we are going to rewrite n. So n is z times x plus y. Z is the sum of the AL. So I'm replacing z by the sum of the AL. And furthermore, I'm replacing the 1 that you don't see here in front of the y by the linear combination of the AL with the CL. Yeah, so this is this equation here. Yeah, so this is the 1 here that I'm artificially multiplying into. Now I can put these two sums together. So this is the sum in L of the AL, because AL appears at both places. And we have x plus CL times y. And x plus CL times y is what we analyzed here. This is this thing. They are non-negative. That's what we found out in the line above. The next step is going to be much more probabilistic now. Namely, we are going to use remark 331. So remark 331 said something like the probability to go from I to I in m plus r plus m steps is lower bounded by first going from I to j in n steps, then going from j to j in r steps, and then going from j to I in m steps. And of course, using induction, you can also, for example, split this thing here now with the same inequality if you want to split the m into, separate pieces. So if m, for example, is m1 plus m2, then of course you can rewrite this in the same flavor, basically. This is what I used in this inequality. So let's look at this computation. Pjjn is the same as Pjj, well, to this power here, because this is what n is. Yeah, that's what we just found out. Okay, so this is the same as n. This is this equality here on top. And now I'm going to use remark 331. So I want to go from j to j in that many steps here. And I can do this by going from j to j, first of all, in a1 times x plus c1 times y many steps. And then again from j to j in a2 times x plus c2 times y many steps, and so on. Okay? In the next step, I use remark 331 again. And for this purpose, I write this number here as AL plus and so on, plus AL. And this has x plus CL times y many terms. Well, now going from j to j in AL plus and so on plus AL many time steps is lower bounded by going from j to j in AL many time steps and then going again from j to j in AL many time steps and so on. And I do this x plus CL times y many times. So this was the excessive application of remark 331. And now we observe that all these factors here in this big product are positive. Yeah, and that's because the AL are in A. Yeah, AL in A means that that Pjj AL is positive. Yeah, that was the definition of the set AL. Yeah, so all of these factors are positive. So if I take them to some power, they are positive, and if I take the product of this, it's also positive. So this was our first and decisive goal, to show that Pjjn is positive for all n large enough. And notice that the n0 tilde, it only depends on j. Yeah, it depends on the set A, and the set A just depends on j, yeah, on the state j. Now recall that the theorem said that Pijn is positive for all n which are greater or equal n0, which may depend on I and j. Yeah, so we have to do this final step now. To see this, notice that you can get from I to j, yeah, because we are in a communicating class, which means that there is an m such that Pijm is positive. Therefore, if we take n greater or equal n0, which is defined by the n tilde 0, and plus the m, then Pijn, again using remark 331, is greater or equal the probability of first going from I to j in m steps and then going from j to j in n minus m steps. And n minus m is greater or equal to n tilde, yeah, because n is greater n tilde plus m. So this thing here, this is greater or equal n0 tilde, which by the argument that we saw before implies that pjj n minus m is positive and pijm is positive by the choice of m. Yeah, so this product is positive, and we are done, because for any n which is greater than or greater or equal this n0, we've seen that Pijn is positive. So this finishes the proof of this technical lemma. On this page, I would like to recall the Euclidean algorithm. If you remember this and if you believe the step in the proof that you saw, then there's no need to go over this. So this has nothing to do with probability. It's just for, well, recalling what you have learned in your algebra lessons. So I don't want to do this in generality, in any generality, or prove anything. I would just like to do this with two examples. So here's the first example. Given the numbers 21 and 27, find the greatest common divisor using the Euclidean algorithm. And the algorithm goes as follows. So take the larger number and represent it as a multiple of the smaller number. So the multiple here is 1, plus a remainder. Then take this smaller number, so the 21 in this case, and represent it with the help of the remainder, which is this thing here. And the multiple here is 3, plus a remainder. And then you continue this way. So you take this number here now, and you represent it with the help of this remainder here, with the help of this 3. So the multiple is 2 here. And in this case, you get remainder 0. And then the algorithm says that the last remainder that you saw is the greatest common divisor of the initial two numbers. Yeah? And you can use the last equation where this remainder appeared and solve it backwards to get the linear combination, or a linear combination of the two initial numbers. So in this case, 3 is equal to 21 minus 3 times 6. I replaced the 6 that I got here. So this is 21 minus 3 times 27 minus 21. Okay, so what I'm getting here is minus 3 times 27, and then I have a 21, and I get a plus 3 times 21, so plus 4 times 21. So I've represented the greatest common divisor by the initial, as a linear combination of the initial numbers. So I'm not going to prove that this works. As I said, it's just this example, and then you will see an exercise with an example. So this is how the Euclidean algorithm works for two numbers. And if you have more than two numbers, then you use the fact that the greatest common divisor of three numbers is actually the greatest common divisor of two of the numbers with the third number. And if you have a representation for this greatest common divisor here as C1a plus C2b, and you plug this in and you get a representation of this greatest common divisor here. So if we call this whatever G, then you might get a representation, say, of this number here as C3G plus C4C. Yeah, C is the one of the numbers that you started with, and then you can put the G back here, and you have a representation of the greatest common divisor of A, B, C as a linear combination of A, B, and C. So all I'm saying here is that you can apply the Euclidean algorithm to two numbers, and you have to do it a few times to get the greatest common divisor of more than two numbers, and also the representation of the greatest common divisor of more than two numbers can be obtained from this algorithm. So this is written down here more neatly, but it's exactly what I just told you. This is not an algebra lecture, but still I would like you to practice this Euclidean algorithm just that you understand what was going on in the last proof. Okay, so here this is a particular example, a greatest common divisor of 46 and 36. Find that with the help of the Euclidean algorithm and find a representation of the type that is used in the last proof, basically. Okay, so let's start with my solution. This is a really great chance to show my inability for concrete computations. So let's see when it gets embarrassing here in this computation. So first thing I have to do is to write 46 as a multiple of 36. So I guess there's only 1 times 36 plus, and the remainder is 10. Then I'm supposed to write 36 as a multiple of 10. So this is probably 3 times 10 plus 6. And in the next step, I'm going to write the 10 as a multiple of 6. Well, this works only once. And the remainder is 4. And next step is to write the 6 as a multiple of 4. This also works once. And I guess the remainder is 2. And now I'm going to write 4 as a multiple of 2. And this works 2 times with remainder 0. So I'm at the end of this computation, and my greatest common divisor is 2. So this was pretty easy, even for me. So the terrible part comes now when we have to solve these equations backwards. So I'm going to write 2 as 6 minus 1 times 4. And then I replace the 4 here with the 4 from here. So this is the same as 6 minus 1 times the 4. So the 4 is 10 minus 1 times 6. And this gives me minus 10. And then I have a minus 6 here and another 6 here. So it's plus 2 times 6. And I'm going to replace 6 by whatever this equation says. So 36 minus 3 times 10. And I'll resort this. So this is the 2 times 36. 36 is already good. And there's a minus 10 here and minus 6 times 10 here. So we have minus 7 times 10. And 10 I'm going to replace by whatever this equation says. And this equation says that it's 46 minus 36. So this is already my representation of 2 in terms of 36 and 46. So I just have to simplify this. So 2 is minus 7 times 46. And then I have a minus 7 times minus 1 times 36, which gives me a 7 times 36. And there are another 2 36 over here. So this is plus 9 times 36. And this is the desired representation of my greatest common divisor in terms of the initial numbers. Yeah? And this is the end of the exercise. And I'm actually quite happy that I had to record this part of the video only twice in order to get this computation correct. This is the end of section 3.6. The question here was on long-time behavior. So what does the Markov chain behave like after a long time? And the focus here was on transient states. And we saw that for a state j, the transition probability Pij to the n, when n tends to infinity, converges to 0. Yeah, so this means that after a very long time, the probability to be at a transient state is very small. Okay, so you see these examples here on this page. So on the left, you see a Markov chain with this red area. And of course, you can spend quite a lot of time in this red area. But sooner or later, you will take this exit, and then you will have left the red area. And you will not return there. Yeah? And in the example on the right, you see the state 2, where you can stay also for quite a long time. But sooner or later, you will switch to 3, and then you will not return to 2. There are other examples of transient states where in principle you could return, but you will not after a random time. Okay. So this was the first part of the section, and in the second part we dealt with a technical lemma which said that Pijn is positive for all n large enough in an aperiodic class. And so this was on the transient case, and as I mentioned in the introduction, the recurrent case is much more interesting, and we'll deal with it in section 3.9. In the meantime, section 3.7 and 3.8 will deal with the notion of invariant measures and invariant distributions and their relations to recurrence and transience, and this will be a preparation for this section 3.9. Okay, so we first need these notions of invariant distributions, invariant measures, in order to formulate the convergence of the n-step transition probabilities for recurrent states. Okay.